All right, I'm back. I'm on page 282, and we're just going to keep going. So we're going to talk about trig limits. So trig limits are weird because, like, very rarely will you find factoring useful because, like, how do you factor sine of x? Like, you basically can't. How do you, like, rationalize sine of x or 1 plus sine of x? Like, what does it mean to rationalize? Like, we still have our Pythagorean identities, Pythagorean conjugates, the fundamental identities, 14 formulas, like all the trig stuff still applies, cofunctions, etc. But trig limits are going to be challenging because unless we know the values, we're kind of stuck. We can think of the graphs, a lot of options. So things that we can rely upon are definitely graphs, definitely calculators. Those are going to serve us very well. Algebra stuff, if we can do it. And then the squeeze theorem. So we talked about the squeeze theorem on some previous page. I don't really remember where. It's like we had to evaluate sine of x over x squared as x goes to infinity. And we set it up and we did it. So I think that if you followed that, you'll follow this. But here's what the squeeze theorem says. It says, assume that for x not equal to c, because with limits, we never care what actually happens at the x value. We just want to get like infinitely close. We're like the annoying little sibling who's like, I'm not touching you, I'm not touching you, I'm not you know, like, and you just like, get away from me. But that's what's happening here. So I'm going to call them L of x and U of x for lower function and upper function, or lower bound and upper bound. So L of x less than or equal to f of x less than or equal to u of x. So L of x is like down here, f of x is here, and then u of x, if I had a third thing, would be up here. So upper is above, lower is below. If the limit as x approaches c of L of x is equal to the limit as x approaches c of u of x, if those are both equal to L, then the lower bound and the upper bound are converging on the same value. Since this is in between them, it must also be converging there. So that's, you might recall, I hate the name, but some people call it the sandwich theorem because it looks like piece of bread, stuff in the sandwich. So that's our squeeze theorem. Usually they're not terribly difficult problems. I talk so long that it's not connecting anymore. I don't know why it does that. Okay, so I'm back. We're moving. All right. So usually the problems are a little contrived and you can just kind of like do them. So we want to show that the limit as x approaches 0 of x times sine of 1 over x is equal to 0. So what are we going to do here? Well, I know that sine of x is definitely always in between -1 and 1, no matter what x is, right? So I'm going to start with that idea. So I know that, so no matter what x, so sine of 1 over x also has to be stuck there because the range is fixed. The thing that you're subbing in is going crazy, especially as you get closer to 0, but the value, the y value, could never be beyond -1 or 1. So sine of 1 over x is definitely in between -1 and 1. Like it has to be. All right, so then what I'm going to do is I'm going to multiply through by x. And why am I doing that? I'm trying to create this. Like I want that to happen. So let me do that. So I'm going to multiply everything I see by x. So then -x less than or equal to x sine of 1 over x, which is less than or equal to x. Okay, that's true. So now I have a function that's always below and a function that's always above. And so what I want to do from here is I want to, it's actually safer to say that it's the negative absolute value of x and the positive absolute value of x. Like we're not trying to do a formal thing here, so don't worry about that. But strictly speaking, it would be better to use those. But I'm not going to do it. Nobody really does it, so don't worry about that. I do know that the limit. So if I take limits now, because this inequality holds, this limit is less than or equal to this limit, which is x sine 1 over x, which is less than or equal to this limit. And I guess I'll put that in parentheses because everything's going in parentheses. Okay, so on the left-hand side, that limit is definitely 0. So this is 0, less than or equal to this limit. We don't actually know yet, But if this limit on the right is also 0, then we do know the limit in between, because it's got to be a number between 0 and 0 inclusive. Like there's only one number that does that. So, and this limit is in fact 0. So therefore, the limit as x approaches 0 of x sine of 1 over x is equal to 0. So let me tell you, it's 2020 right now, like the year 2020. And on last year's AP exam, 2019, there was a question that actually required you to use the squeeze theorem to show that a limit had to be a certain value. And basically it was a continuity question. You're like, is the function continuous at this value? And for some reason you knew the value of the function, and then there was enough information to use the squeeze theorem, and that, like, it just murdered people. People were unprepared for that, but you are not going to be unprepared for that because you know the squeeze theorem. Just think about it every once in a while. Every once in a while, like, you should make a list of things that, like, every once in a while you just want to spend a second or two thinking about. So the next thing we're going to do, we're going to actually skip some proofs, partly for time. We skip them every year, and then in calculus, it turns out we don't really need them, but if we did, we could prove them then. The proofs, if we needed the proofs, we could prove them, but I'm going to skip it for now. What I am going to do is I'm going to switch over to the calculator and figure out what these two limits are. So sine of x over x as x approaches 0, and also 1 minus cosine of x over x as x approaches 0. So we're going to figure these out using the calculator, and then we'll be done with this page, and we'll come back and use it for other stuff. Here's some calculus stuff. Someday you too will be doing this. All right, so how should we figure them out? I'm going to start with a graph because you always want to start with a graph. I know that the CAS can just find limits, so you're tempted to just use the template all the time. It's more fun, though, if you actually look at graphs. And we've seen this graph before. So for this particular graph, I think it's at the beginning of some set of notes. I don't know where it is. It's in the notes at some point, though. So what should I do? I'm going to trace. Right? Try to trace a 0, undefined. But look at that thing. If I put in 0.0001, I get 1. That's very close to 0, and I get 1, or very close to 1. It's actually rounded. Negative 0.0001. I get 1. I think there's compelling argument here that this limit is 1. So let's just graph 1. Ooh, I'm pretty sure that's 1. Now, having investigated it graphically, let me look at a calculator page. Let's take the limit, right? So template, limit as x approaches 0 of sine of x over x. I get 1. So this will in fact be 1. I'm going to fill it in the notes in a second. I will also point out that if the limit of sine of x over x is 1, then the limit of x over sine of x is also 1. That's one of the properties of limits. As long as the limit is not 0, then the limit of the reciprocal is the reciprocal of the limit. So if the limit had been 8, then the limit of the reciprocal would be 1/8, for example. Obviously not relevant here, but just a random example. Let's take a look at the graph of the next one. So doc 4, I'm going to add, I'm going to keep it, same problem, it doesn't make a difference. So 1 minus cosine of x. This graph is not as famous. I don't actually offhand know what it looks like. I know what the limit is, but let's see. Ooh, yeah, so look at that. That limit, definitely 0, right? So from the left, 0. From the right, 0. Limit is definitely 0. Let's see what the calculator has to say. Click here. If you want on the handheld, you do Control and then to the right, Control and then to the left. We'll move you like back and forth. There's also, if you Control up, you get this page sorter view, and then you can just arrow through them and decide like where you want to go. Press Enter. All right. So since I also want the limit as x approaches 0, I'm just going to steal that, delete that. 1 minus cosine of x over x. I'm expecting 0, and I get 0. Since this limit is 0, we don't know anything about the limit as x approaches 0 of the reciprocal of x over 1 minus cosine x. No idea. But sine of x over x is 1, which means x over sine of x will also be 1. So I'm going to go back to the notes and fill in those things, and then call it a video on this one. Let's see. So here we go. All right. So here we are. We have found that the limit as x approaches 0 of sine of x over x is 1. Okay, so you got to memorize that. It's a very famous one. Later on, you'll learn like a bunch of things. Like if you think way back, at some point I told you that sine of x could be written as, are you ready? X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. It's just going to keep going, like all the odds over the odd factorials, and it alternates. Try putting that in the numerator and dividing out the x and see what would happen if x is 0. It's a really fast way to remember this one. Hint, you'll get 1. And then here we got 0. The only other thing that I want to mention here is that because this limit is 1, we also know the limit as x approaches 0 of x over sine of x is 1. So we know both of those. All right, yeah, so we're not going to prove them. We did, I think, using a graph, using the calculator, that's like very close to a proof. And it's like a modern day thing. Like I'm satisfied with that. Like I don't feel bad about having done it that way. And so I hope you also don't feel bad about it, because we're not doing it another way. If you're interested, you can look them up for sure. But anyway, I will be back in the next video to do more stuff. See you then.